Welcome. So we want to find the electric potential, but we want to find the difference of electric potential. And if we know the electric field, we can do this. This is a different way than the summation method. This is what we call the path integral method because we are going to find the electric potential along a path of electric field. So our first step for anything in Sketch Organize Solve is obviously sketch. So we want to draw the charge distribution. So we're going to assume a electric cylinder, and we're looking kind of along the side of it instead of at the face of it. And then we want to draw the starting and ending points. So we are going to say that we are going to go from this place initially to this place finally. So that's our starting and ending points. And lastly, we want to draw the electric field at useful places. So if we're assuming that this is a positive cylinder, what might be useful is the electric field at the final moment will be radially outward. Initially will be radially outward. And so we kind of have some radially outward and then getting a little bit smaller. So we want to visualize what's going on with this field. And so what we want to do while we are doing this is we want to then choose a path where the electric field and the path segment, we're going to call this path segment ds, are either perpendicular or parallel. We can't do this with one path like we have here. We want to break it up, the path, into segments where we can. So in this case, I want to be moving where my path at this point is anti-parallel to the electric field. And then I want a radial path. So at this point, my ds is going to be going in this direction, ds in this direction, but along here, my ds is going to be perpendicular. So if I choose this path, then I'm going to have this one straight path and this one arced path. So in this organized step for delta v equals negative integral E dot ds, my integral of E dot ds is going to be along path A, right? The electric field of A dotted with dsa plus the integral over path B of the electric field of B dotted with dsB, and so on and so forth, right? If I have multiple sections, usually we can do this with just two, maybe three path sections. And so if my electric field is parallel to the ds, then I have my integral E dot ds is equal to the integral of E along a face times dsa along the face. If they're anti-parallel, then this dot product introduces a negative sign. And if my electric field is perpendicular to ds, then the dot product will be 0, or this electric field E dot ds is equal to 0. And so what's nice about this is then my electric field will be from a known, or will be a known quantity. So in this case, I can look up, or I'll be given the electric field. So for the ds, my ds will be equal to dx dy dz for a straight path, and my ds will be r d theta for an arced path. So in this case, along here, this is going to be dx, and along here, this is going to be r d theta. But more importantly, right, this is 180 degrees, so I'm going to have a minus sign here. This is going to be 90 degrees, and so this entire section will be 0. So in this solve step, I only have to worry about one of these, and I've reduced any sort of directions because I've chosen a parallel path. I still do have to take the integral of my known electric field and then whatever my path may be, right? Establish bounds and evaluate the bounds. And any other further simplification needed.